spectrum determines all energy in life, all the energy that we use in any way, shape, or form. So today's class, or the classes here, they're requested to talk about a multimeter. Well, multimeter is like saying a car. What kind of car do you want? A big one, a little one, a blue one, a green one, or whatever. So when you say meter, you might define the kind you want. But a multimeter, there's many kinds of multimeters, and they read different types of signals. So let's just look at the paper there. The main thing is that we've got to start learning in our children too, is that in the old world, the analog world that we lived in, most things were big. Our cars were big, our batteries were big, et cetera, et cetera. So we went from 0 to 10 to the 6th power, which is 1 million. Okay, now actually with computers, we've gone above 10 to the 6th power. But now with the new digital world, things are getting smaller and smaller and smaller. So now you need to learn at least down to 10 to the minus 6. So this is a very good chart, I think anyway, on there. And if you start at 1 meter, 1 meter equals 1 meter. And if you put in your head, it's easy kind of to remember ham radio operators operate at a 1 meter band. So that kind of gives you an idea of who's going to use this, okay? So a micrometer, okay, after the meter, then you have a millimeter, which is 0.001, okay? A micrometer, which is 3 zeros with another 001. So it's a very easy way to go over that. Nanometers, when we get to computers, we're going to be talking a lot about nanometers. And then 00, 3, 0, 0, 2, 3 zeros, and then the final one is 001. So, and then you get up now with computers into picometers. And this projector here, that's called a pico projector. So you're down into that range when you get to some of these devices. So, and then a kilometer, we had trouble with that yesterday with the teens in the class. A kilometer is 1,000 meters. So, anybody know what a meter is?
Yeah. You mean distance-wise?
Yeah.
A little over a foot, a little over a yard, 39 inches.
39 inches, right. So it's almost a little bit more than a yard. Okay. So we were talking about yesterday with your speedometers on a car. The speedometers have a kilometer and they have miles per hour, kilometers per hour. So much of the world does not use the metric system that we use. So when you set up, like when I set up some of these programs this weekend that I'm going to use this week, I have to choose in my mathematics system which I want to use. So what are we using?
But we're not using metrics.
What are we using?
We're using
It's based on a king of England, so his feet, and so on. So it's called imperial. So when you set up the computer, you're going to have two choices. If you want imperial, which is inches, feet, gallons, and all that kind of stuff, or you're going to set it up for metric system. The metric system is based on 10, 100, 1,000, 10,000, and so on. So that's what I was trying to get to the kids yesterday, and they had a little trouble.
well, I thought the imperial measurement was still a third type of measurement, because when you go up to Canada or parts of,
Right.
other countries, it seemed like the imperial gallon was different than a gallon that we know.
It was a quart larger.
Yeah. I don't know.
Either a quarter or a pint.
All I know that
I think it's
when you're dealing with the computer anyway, in science, you usually have two choices. The
Okay.
imperial system,
Yeah.
which means inches and feet,
okay.
so, or the metric system. I don't remember any other choice recently anyway. So, but again, that's one of the problems with the imperial system. It's a foot of some king from England. Now you're bringing up another point. I probably should talk about it. It's on the subject, but it's off of say a foot or a gallon, what do we mean?
Volume?
Let's say a foot.
Length or volume?
A foot. Okay. And this comes in the realm of statistics too. When you say a foot, somebody has determined what a foot is, some expert in the world. Okay? Then they come up with a standard of what a foot is. And that standard is where? Anybody know? It's in France. Okay? It's a standard, so I don't know if the company or government supported or what, or worldwide supported, but there's something there that's a bar that is 1 foot long.
Yeah.
And then people from around the world go there and take a measurement. Let's say they go once a year, get a measurement. Let's say the United States goes there. Then we have the Bureau of Standards in the United States, and they have matched it against that. Then they bring it back to the United States, and then that becomes a standard for everybody in the future. Okay? Then you roll that down to the ruler that you and I buy at Office Max. So, but I'm saying there are the maximum standards, the real standard, the substandards around the world by a country, and so on. So, bottom line, it seems to me that what you're saying is, as you get down the line, people could change the gallon. It seems to me that Canada could have a different gallon than we do if they wanted to.
They
It's
do.
the universal standard is the universal. Then you come to the company standards, and then as you move down the line, I presume a company could make whatever's convenient for them. I don't know that to be fact, but it just seems to me
Don't the
that.
states require, don't the states measure require pumps, they go and check them every year or so. With a
Yeah,
sticker on it.
weights and
Standards
measures.
department, yeah, they keep an eye on it, they can't change that.
Yeah,
But
it's weights, the standards on weights and everything, so all I'm saying, there's a universal, universe standard,
Yeah.
or a global standard, and then each country theoretically goes there and gets their standard, and then from there, let's say Ford Company and GM will get their standard in their engineering department, and from there flows everything else.
but on that gallon.
It's called the Bureau of Standards.
They referred to it, like in England anyway, it was called an imperial gallon. And different.
Well, we can look it up, but I'm saying, that in my mind, imperial is what we're using.
It's a generic term.
No,
Or what are we using?
I don't know what the
I
standard
think
of
it's
the
right,
US
Jack.
gallon
I
is.
think in the world that he's talking about, I think he's probably right. It's imperial versus metric.
Well, I know when I set up these flight programs for the drones, okay, we just sent one up over the weekend there, and I set one up a couple of weeks ago, and they sell them all over the world, drone programs. Okay? You only have 2 choices, imperial or metric.
Well, all I know is that when I was over there buying gasoline, the English gallon was more in volume than
Yeah.
what we were used to.
Well, that's what I'm saying.
Yeah.
I'm saying, as the standard goes down the line, from the world to a country to a section and so on, these people, I presume, could change their standard, but it still comes from the national standard. So the Canadian gallon, I would presume, could be different than ours, different than England, if they wanted it. And a lot of this is decided by, it's an IEEE, Institute of Electronic Engineers from, anyway, a lot of these people meet once a year somewhere in the world, okay? And then they set up these standards, like ASCII standard, all the standards we have in here. ASCII standard, the ANSI standard, and so on. And then, if you don't want to follow them, you don't have to. But if you want my computer to work with your computer, or the Japanese computer to work with the German, you pretty well have to follow them. So, anyway, let's get back to here. If you look at the electromagnetic spectrum, there, it starts way down here. Okay? See it? Starts with 1 picometer. And then it goes up, those are gamma rays, which we don't really get a lot of in the world. But they come, gamma rays come down from space. And then X-rays we do use. X-rays are the X-rays that we use in the hospital. The X-rays go from 1 picometer to 1 micrometer. And then in the middle there is a nanometer, and that's your ultraviolet. You all know what ultraviolet is, right? The kids use it for the dark thing, they put an ultraviolet light on, their t-shirts light up, all kinds of things light up. We used to use it in bathrooms to sterilize the bathroom. We don't see much anymore. But then you come to the visible light. The visible light is what our eyes can see. Then above that, and that's 1 micrometer. Above that is infrared. Now in my house, I have a little device that I can watch my studio and I can watch my camper from my house with a TV security system. So when the lights go out, I can still see that room just as well as I saw it before with infrared. So they call that the near infrared. So we use it for seeing in the dark, basically. It will not be color because you're out of the color spectrum, but you moved up, but you're not far enough away that some of these devices that see light can see it. Okay. Then you go to 1 mm. That's where your microwave starts. Microwave are these towers that you see around that look like this. They're parabolic, they're sitting on top of hilltops, and they look at each other. And they have to, it's line of sight. They have to go from here right into there. You can't go like that, but they don't see each other. So that's what they call a microwave. And that's why our police used to use, our fire departments, like from here to Temple or whatever. So you see a lot of them on hilltops. Then you get to the 1 meter band. 1 meter band, as I said, a lot of ham radio operators can use that. Then you go up from there, and there you see above that is your radio waves. Now, if you go to the chart down underneath here, this is only an example of how some of this energy is used by our body. We're going to get at the other part of it very quickly. But we've already gone through color quite a little bit in our class in the last 6 months or a year. Okay? So your eyes see color, and this is how they see color. Okay? If you look at your spectrum, you got 400, 500, 600, and 700. So within the spectrum there, if that wavelength is 400 nanometer or 700, they're going to be different. 400 will be down in the blue range. 700 will be up in the red range. Okay. And in photography, those of us who've been around a while, you know, used that film for Kodak A and B light, skylight, 6,000 Kelvin is the way it was measured. Indoors, red light from incandescent lights is 2,800 Kelvin. So that's where you'd have a light bulb that's white and then one that's blue to compensate for all this. Okay, this is the response of the human eye. And this, Jack, if you remember, becomes very important when we get into astronomy. Astronomy, you're in the dark, you only see in white and black very frequently. When you get to the nebulas and so on, they're all colored and so on. So in astronomy, to the eye, you have cones, which we won't go over today, but cones and rods in the eyes. Some of them see color, some do not see color. So in astronomy, sometimes you have to look with what they call averted vision, where you're not looking straight at it. You're using the part of the eye that sees black rather than the part that sees color. Any questions on any of that? That's kind of just the basis. So what I want to do is and we're trying to do is keep bringing up this micro world that we're living in. So basically, in my opinion, the body to me is the perfect machine. There's nothing that humans have been able to make, in my opinion, better than the body. Okay? Therefore, I love studying the body. That's why I went into medicine. It lasts 100 years, okay, more or less. 85 for sure. There's no car that I ever bought lasts that long. There's no truck I ever bought lasts that long. There's very few of my devices that last that long. Plus, it will regenerate itself. So if you lose some tissue, you can make that tissue over. So what we're going to talk about today is electronics, the electronics of the body, which is one particular part of it, which is the most important part of the body, the heart, right? When the heart starts beating, it's got to beat in a certain way for 100 years. And it doesn't stop, usually doesn't skip a beat until you have some kind of problem. So that machine will do that for 85 years. So anyway, here's a model of the body. So for this part of the anatomy and electronics, we're talking about what we call the heart-lung machine. It's a heart-lung machine, and they must work together. So this is your heart. And you can pass that around. Now you have a heart in your hand.
Have a heart.
Okay, let's get back to the magic circle. We have used the circle, and not only me, but science does, and we should teach it to our kids in school. A circle can give you a lot of information and bring it together. We have short-term memory.